Hello, today we're continuing in our series on particle physics, looking in particular at annihilation and creation operators and introducing the idea of mass. Last time we looked very simply at the idea of quantum field theory, and I kept it simple so that this is an access point so that you can all find out more by looking at other videos or books. But we developed two field operators, and that was psi dagger and psi. Psi dagger is essentially the field creation operator. It consists of a plus, which is, as we showed, a creation operator, and a field. And the annihilation operator, which consists of, this is a field annihilation operator, which consists of a minus. We developed what that was last time. And a field. This is the field term. This is a sine and cosine wave. What is k in all of this? Well, remember that k is simply the what's called the wave number, and it is defined as being 2 pi divided by lambda, lambda being the wavelength of this wave. But we also showed that p equals h bar k, where p is the momentum, and so if h bar is 1, and we often set h bar is 1, you'll find that in this series, in order to get constants out of the way, we set them to equal 1. So h bar and c, the speed of light, will often be simply regarded as 1, and so we don't need them cluttering up the formula. If you set h bar equal 1, then p equals k, and that means that this term k is really just, this term k here and this term k here, these are really just proxy terms for momentum. So what these field operators are doing is essentially creating a particle with a momentum k, or annihilating a particle with momentum k. So let's now consider particle scattering, and I'm going to draw what's called a space-time diagram. So time goes along that axis and space along this axis, keeping it one-dimensional, of course. And I'm going to have a target which I'm going to place at space position x equals 0. In other words, it stands still, but of course it travels through time. Everything travels through time, but it doesn't move spatially. It just travels at the speed of time through time. And what we're going to do is to scatter a particle off of that target. So here comes a particle, and it has a momentum ki, k initial. K, remember, was the proxy for momentum. And that particle is scattered off of the target with a different momentum, kf, k final. And the target may well recoil. There may be just a slight movement, barely perceptible, because the target will be massive compared to the mass of the particles. But essentially the target absorbs any difference in momentum. So what do we do with this diagram as far as quantum mechanics is concerned? Well, it's fairly straightforward actually. What you have is you start with a particle in state Ki, that's this particle here, and you produce a particle in state Kf, that's this particle here. And how did you do that? Well, you, in quantum mechanics terms, field quantum theory, what you do is you annihilate this particle, so you apply the quantum field operator that will annihilate Ki, and then you put in the quantum field operator, the creation operator, that will create Kf. And in terms of quantum field theory, that's what has happened. This particle has been annihilated, this particle has been created. That doesn't necessarily mean that this particle has somehow vanished and another one has been created. But in mathematical terms, that's how we represent the scattering. The incoming particle has been annihilated, the outgoing particle has been created. So if we put that in terms of the mathematics that we developed last time, what we can say is that this term, the psi dagger psi, will be, of course, the sum over k of, a plus k e to the minus I kx minus omega t. And this psi will be sigma over k a minus of k e to the plus I kx minus omega t. And that will all act on the state Ki. Now it turns out that because we've got a time term in here, and because you don't know where this is going to happen in time, you have to integrate over time in order to get the full effect. And that acts on Ki to produce Kf. There is also, I should just say, what's called a coupling constant. I'll just squeeze it in here. Coupling constant G, which we won't need to bother with. It's also there as well, but that's not going to be any relevance to us at this stage. We're really interested in the total integral. And we learnt in quantum mechanics concepts of the inner product, which we wrote like that, and we said that an inner product of a ket vector with a bra vector, x and y, means this is simply the probability amplitude that if you prepare something in state x, this whole term gives you the probability amplitude of finding it in state y. And the probability as a whole will be the square of the probability amplitude. This was all described in great detail in my series on quantum mechanics concepts. So if this is not familiar to you, I suggest you go and look at that series so that you can see where all of this comes from. It's all explained very clearly. So consequently, what we can say is that I'm not going to worry about the probability. It's sufficient to look at the probability amplitude. The probability amplitude of taking a state in Ki and finishing up with a state in Kf, the probability amplitude of starting here and ending up here is going to be given by this inner product, but in the middle of this inner product we're going to have to put this entire term here. So that entire term there sits in between, because that is the term that acts on Ki in order to produce Kf. Well, think of going back to the first of the videos that I did in this particle physics series. I told you what the effect of A minus on Ki would be. Remember, in this term here, the A minus term is cycling over the values of K. In a little while we'll see that there are only allowed values of K. So this is cycling over allowed values of K. And for most values of K, it is looking for a particle to annihilate, and there won't be one. The only particle that exists to annihilate is the one that has a particular value of K, which is K initial. So this will cycle over all the values of K and do nothing until it gets to K equals Ki. And when K equals Ki, A minus will annihilate it. So what you will end up with, the effect of A minus on Ki is to annihilate and give you the vacuum. And that's the state 0. We also showed what the effect of A plus acting on a bra vector is. A plus essentially is the reverse, and A plus acting backwards on a bra vector Kf also produces the state of the vacuum. A plus, of course, acting on a ket vector will produce a particle, but A plus acting backwards on the bra vector we showed produces the vacuum. So now we've got the inner product of the vacuum with the vacuum, and the inner product of anything with anything else, anything with itself, inner product of anything with itself is equal to 1. So this inner product is simply going to be equal to 1, and we can therefore largely discard it. What have we got left? Well, the A minus has now gone because we've acted on Ki, and the A plus has acted on Kf to give us 0. So the only thing we're now left with is the integral over time of the exponential terms. And the exponential terms are this ones and these ones. Now you'll remember that in the experiment I set x equal to 0, which I'm entitled to do, because that will make the maths easier. So now when I do the exponential, the x terms can both be set to 0, so that doesn't count at all. And the only thing that I'm left with now is e to the I, this omega t term, where that omega is obviously associated with the initial, so that's going to be minus omega initial, and this is going to be minus times a minus omega, and that's going to be associated with the final term. So I'm going to get e to the I omega f, which comes from here, because that's a minus times a minus, so that's a plus omega final, because it's associated with the final term, minus omega initial, which comes from here, that's the plus times a minus as a minus omega, and that's associated with the initial particle, t. And that's all that's left. So we've got this integral over time of that exponential. The k, remember, went because x is equal to 0. Now, if omega f equals omega I, then this term here will be 0, and the exponential will therefore be 1, because the exponential of 0 is 1, and you simply integrate 1 over time. That's doable. What happens if omega f does not equal omega I? Then there will be a number in this term here, and that means that you will have the combination of a cosine wave and a sine wave. And the integral of a cosine wave or a sine wave over time is equal to 0 for a whole wavelength. Why? Because, let me just draw, here's a sine wave. You could equally well draw a cosine wave. That's one complete wavelength. And what is the integral over that wavelength? Well, the integral, of course, is just the area under the curve. And there's a positive area here, and there's an equal negative area here. So the integral over a whole wave is 0. So when omega f does not equal omega I, this term, the exponential, becomes 0. Therefore, the whole integral becomes 0, because it's integrating nothing. So the only time this integral has any value is when omega f equals omega I. And I can multiply each side by h bar. So I've now got h bar omega f equals h bar omega I. And you should recognise that h bar omega is an energy term. And that means that the final energy is equal to the initial energy. And so we've shown that in the quantum mechanical application, we have derived the conservation of energy. The final energy is equal to the initial energy. Now let's think about particle decay. Here is an incoming particle, which I will call K1, so it has momentum K1. And the particle is going to decay into two other particles. One I'll call K2, it has momentum K2, and one I'll call K3, it has momentum K3. Remember, K is a proxy for momentum, because momentum P equals h bar K, and if h bar is set to 1, then P is essentially the same as K. So here are these particles, one comes in, and at this point here, it decays into two other particles. So the way we represent that diagram quantum mechanically is, of course, we say that we have a state K1, which will become the state K2 and K3. And how will that happen? Well, you annihilate with the field annihilation operator K1, and then you apply the creation operators. There are two of them because you're going to create two separate particles, K2 and K3. And that's essentially all there is to it. And using exactly the same arguments as we did before, we will say that the probability of getting states K2 and K3, when you start with state K1, this is the inner product. Remember, that's the probability amplitude. It's the probability amplitude if you start with K1 that you will end up with K2 and K3. And of course, in the middle, all we have to put is the two creation operators and the annihilation operator. That's these here. This time we're going to have to integrate over all space. It's all going to happen at a particular time, but we don't know where in space this is going to take place, so we're going to have to integrate over all space. So once again, we're going to have to write out the effect of all of this. And so what I'm going to do is to put, because I don't think it'll all fit across one line, so we'll probably have to stretch across two lines here. So I've got K2, K3, then I've got my integral term, dx. Then I want my first creation operator. Well, that's going to be sigma over k, a plus of k, e to the ikx. I'm not going to bother with the omega t term because it's all going to happen at one time, which I can set to t equals 0. So we can forget about the time coordinate here. That will shorten the process a bit. So that's the first creation operator. Here's the second creation operator, which is sigma over k of a plus of k e to the ikx. That's the second operator. Then I need to operate with the annihilation operator, so I'm going to come down here and we need to multiply by sigma over k of a minus. Incidentally, those should have had minus terms there. Of course, I forgot that. This is the creation operator, so it has e to the minus ikx. Coming back here, we now need the annihilation operator, which is a minus k e to the plus ikx, and that acts on the state ki. So this double line is the full term for the probability of starting with ki and ending up with k2 and k3. Once again, we can use the same argument that we did before. Here we can say that we're going to cycle over all the valid elements of k until we get to ki, and when we get to ki, a minus of ki will kill ki. So in other words, it will simply produce the vacuum state. So when k is equal to ki, a minus of ki hits ki and produces the vacuum state. For all other values of k, it does nothing because there's nothing to do. Similarly, this A plus will hit K3 bra vector to produce the vacuum, and this A plus will cycle and hit this K2 and produce the vacuum. So the consequence of the two A pluses acting on K2 and K3 is to produce the vacuum on that side. So once again, we're ending up with the inner product of the vacuum with itself, which is just going to be 1. And then in the middle, we've now got the integral over all space. We've got rid of all the creation operators because they've done their job. So we're now just left with the integrals. This k is obviously associated with k1. That's the initial state. This integral is associated with k2, and this is associated with k3, because this is what annihilates k1, this is what creates k2, and this is what creates k3. So what you'll find is that you're left with the exponential to the minus I of k1 minus k2 minus k3 times x. That is the effect of bringing together all of these exponentials. And for the same logic as we had before, if k1 minus k2 minus k3 equals 0, then the exponential will equal 1, and then you integrate 1 over all space. But if k1 minus k2 minus k3 does not equal 0, then the integral over a whole wave will be 0, and therefore the whole term just disappears. So this term only has a validity for exactly the same reason as just a few moments ago. If k1 minus k2 minus k3 equals 0, k1 minus k2 minus k3 equals 0. If it doesn't, then the integral over a whole wavelength or any number of wavelengths will be 0 and everything disappears. And if that's the case, then k1 equals k2 plus k3, which says that the initial momentum is equal to the final total momentum. And that way we've just shown that momentum is conserved. So far we've just been talking about any old particles. But now I want us to focus on fermions. You'll recall that there are two types of particles in the whole of this universe, and only two are known: fermions and bosons. Fermions are the things of which what might call the genuine particles are made, things like electrons, quarks, neutrinos. Those are all fermions. Whereas bosons are things like photons, the W and Z bosons, gluons, and possibly even gravitons, and of course the Higgs boson. Those are all bosons. Now the essential difference between fermions and bosons is that the Pauli exclusion principle applies to fermions, but it doesn't apply to bosons. And why does that matter? Well, the Pauli exclusion principle says that those things, that's fermions to which it applies, you cannot have more than one particle in any given energy state. Whereas with bosons, you can have as many particles in a given energy state as you like. And so since everything tends to want to go to the lowest energy state, when you've got bosons will all fall to the lowest energy state, and billions can occupy that same low energy state. It's called the Bose-Einstein condensate, and I've dealt with that in a separate video. But when you get to fermions, one fermion, say an electron, one electron can occupy the lowest energy level, but then when the next electron comes along, it cannot occupy that level because it's already occupied. It has to occupy the next one up. That's the critical point. So let's just remind ourselves of what we've shown several times before. This is an electron orbiting the nucleus. And in order to overcome this problem, that the classical expectation is that because the electron is radiating out energy, it will spiral into the nucleus and the whole atom will disintegrate. In order to solve that problem, we said that you actually regard the electron not as a particle which is orbiting, but as a wave which acts as a wave around the nucleus. And the thing about that wave is that it's a continuous wave, which means that it's joined up. There is no discontinuity from the start point and the end point. It just continues to go round as a wave in this orbit. And the radius will be, let's say, r. And that means that there is an exact number of wavelengths. The wavelength is the distance between two consecutive peaks. There will be an exact number of wavelengths in the entire circumference of the orbit, and that circumference, of course, is just 2 pi r. Remembering that lambda is 2 pi over k, that's essentially the definition of k. K is 2 pi over lambda, so lambda is 2 pi over k. We can now substitute lambda in here. So we get n 2 pi over k is equal to 2 pi r. The 2 pi's, of course, are going to cancel. And then that simply gives you that k is equal to n divided by r. And n is a whole number because it's an integer number of wavelengths. So n is a whole number. And that means that k is what's called quantized. It can only have integer numbers of 1 divided by r. So k cannot just be any old value. It is restricted in its positions. And since, as we've said before, p is equal to h bar k, and we tend to set h bar equal to 1 so that p equals k, if k is quantized, then so is momentum. That means the electron in orbit in an atom cannot just have any old momentum. It is restricted to specific values of momentum. So k and p, momentum and wave number, are quantized. So let's draw the, as it were, the k scale. And what we've just shown is that k cannot just be continuous. There are discrete values of k that any particle can occupy. And we'll think about electrons because they're fermions. We're thinking about fermions, not bosons. And let's just remind ourselves that E, the energy, is, well, in terms of kinetic energy, is p squared over 2m. That's another way of writing half mv squared. We've shown that before. And since p equals h bar k, if you make h bar equal to 1, the old trick, then p equals k. So energy is k squared over 2m. Because, as I said, p is equal to h bar k. And we're doing the trick of setting h bar to 1 to get it out of the way. And so p squared is equal to h squared. So energy is essentially proportional to k squared. So since fermions, since electrons will want to occupy the lowest energy state, what that means is that they will also want to occupy the lowest k state, because that is equivalent to the lowest energy state. So when a fermion comes along and wants to occupy a k state, it will sit at the lowest value of k. When another electron comes along, it cannot occupy that state because it's full. Pauli's exclusion principle says no, you have to occupy the next lowest energy state. and so on. As more and more electrons come along, these could be states in an atom. If you've got lots of electrons in an atom, they can't all occupy the same orbit. They have to have their own energy orbit representing their own value of K, and so they will continue to fill up increasing values of K, increasing values of energy, increasing values of momentum, until all the electrons in the atom have been accommodated. Now, we do know that, of course, it's perfectly possible for a photon to come in. This is a photon with a certain amount of energy, and it hits the electron. It transfers its energy to the electron and promotes the electron up to a higher energy level. So it's no longer here. It's been moved up here because of the energy of the photon. But after a short while, that electron will want to fall back to the lowest possible energy position. It can't go to the very lowest, it can only go to the available energy position, and in doing so it will emit a photon with a certain energy. The energy, of course, will be the difference between the energy at this point and the energy at this point. All the electrons which are already filling K levels are called the Fermi sea, named after Enrico Fermi, who was a key physicist involved in all this work. Now, before we progress, I want to just remind you of the wave equation. If we take a wave, psi is equal to, here is the most basic form of wave we've used, e to the I kx minus omega to c. I did a video specifically on the wave function. You can look at that, and this is about the most simple form of the wave function you can get. And what we do is we do the derivative of psi with respect to t, and if you differentiate this term with respect to t, you bring down the term in front of t, which is minus I omega, because it's I times minus omega. So that brings down minus I omega, and then you leave this term as it is. Well, this term is equal to psi, so I'll just put psi there. Similarly, if you differentiate with respect to x, so d psi with respect to x is, this time you bring down the ik and leave the term as it is, so it's ik psi. And now if I divide both sides of this equation by minus I omega, I will get psi. And if I divide both sides of this equation by ik, I will get psi. And so those two will be the same. So what I'm saying is that d psi by dt times 1 over minus I omega, which is this term where both sides are divided by minus I omega and leaving just psi on the right hand side. That's going to be equal to d psi by dx times 1 over ik. That's this term divided on both sides by ik, leaving just psi on the right hand side. So these two terms must be equal, which means that d psi by dt is equal to minus omega over k d psi by dx. Oops. And if you want to, of course, you can leave the i's in, but I'll take them out at the moment. The two i's obviously will cancel, but a little bit later on we'll be putting them back in, you'll see why. But just for the moment, let us just remember that omega is 2 pi f, 2 pi times the frequency of the wave, and k is 2 pi over lambda. That's the definitions of those two terms. So omega over k is going to be 2 pi f divided by 2 pi over lambda. The 2 pi's cancel. And so you've got omega over k is the frequency times the wavelength. And what is that? Well, that is one and the same thing as the velocity. If this were photons, then of course this would be the velocity of light, which would be c. But we're now concentrating on electrons, which do not travel at the speed of light. So now we've got that d psi by dt is equal to minus v, where v is the velocity, times d psi by dx. And that is known as the wave equation. Now, I just want to think for a moment about this wave that I chose to use. Psi equals e to the I kx minus omega t. And I want to ask, how is that different from this wave? psi is equal to I kx plus omega t. What's the difference between those two waves? The answer is that this is a wave which will move to the right in time, and this is a wave which will move to the left in time. What do I mean by that? Well, if you plot, I shall call that, therefore, that's psi right, that's psi left. It means it moves to the right or moves to the left. What do I mean by that? Well, let's just draw one complete wavelength of the psi right term, and that is what the wavelength looks like when t equals 0. If you were to plot that curve at t equals delta t later, you would find that the wave has moved to the right. Right? So essentially that wave moved to the right in a small time delta t. Whereas if you take this wave psi left and you plot it at time t equals 0, and then you go delta t later, you'll find that that wave will now be slightly to the left. In other words, it's moved to the left. So this is a wave which in time moves to the right. This is a wave which in time moves to the left. And so if we produce the wave equation, well, the one we just produced, which was essentially for psi to the right, we said that d psi by dt is equal to minus v d psi by dx. That's for the right moving wave, so I'll put sub letter R for right. You should be able to see that if we had done the same for psi left, we would have got plus v d psi left by dx. Because here we had a minus term, that's what brought down the minus omega, and that's why we ended up with the minus v. Here we've got a plus term, that would bring down a plus I omega, and consequently you get a plus v. So the wave equation differs depending on whether it's a right or left moving wave. And that means that, of course, that v is equal to plus or minus omega over k, depending on whether you bring down the minus term for the right moving wave or the plus term for the left moving wave. So suppose I now draw a graph of omega against k. Now remember that omega is essentially a proxy for energy, because energy is h bar omega. And if we set h bar equal to 1, which of course we're constantly doing, then energy is omega. And that means that this is essentially an energy term. K, you'll remember, P equals h bar k. And again, if you set h bar equal to 1, then P is k, so k is a proxy term for momentum. So essentially you're plotting energy against momentum. But omega divided by k gives you the velocity. So I can plot the velocity term like this. This is the graph of omega over k, and that graph will give me a gradient, which is a positive gradient, so that's the plus v term. Equally, I can plot the negative v term, which is omega over, and these are negative values of k, so I've now got a minus v term. What Paul Dirac, sometimes affectionately known as Pam Dirac, because his initials were P-A-M Dirac, but his actual name was Paul Dirac, a brilliant physicist and expert in quantum mechanics, someone who took up the challenge very early on. What Paul Dirac said was, why have we stopped at the origin? You know, it's perfectly obvious when the omega is 0, k is 0, and that's presumably the place at which you stop. But Dirac postulated that you should be able to continue this line, and you should be able to continue this line. Now, you might immediately protest that this is not possible, because as soon as you get into the dotted lines, you have got into the minus omega territory, because this is now where omega is minus. And if omega is minus, then so is energy. It means you've got into negative energy. And who's ever heard of negative energy? So, sorry, Paul, you can't do that. That must be a nonsense. But Paul Dirac is unperturbed. He wants to pursue the possibility. So now we raise the next objection, which is if you do extend this line, you can extend it to minus infinity, because there's no reason to stop anywhere earlier. And if you do that, that means that k will extend to minus infinity. And when you come to putting electrons into their allowed levels, remembering that k only has allowed levels, there will nonetheless be an infinite number of allowed or discrete k levels in the minus k domain. And that means that electrons will constantly fill up minus infinity plus 1, minus infinity plus 2, which of course have no real meaning, but you get my point, that the electrons will just constantly fall down to the lowest k level, which now, according to Dirac, is minus infinity. And so there will never be an opportunity for electrons to occupy a positive k value, because they'll constantly fall down to an infinite number of available slots in the negative realm. But we do see electrons with positive energy, so this must be wrong. But Dirac, undaunted, speculated that all these negative energy, all infinite number of energy levels represented by the discrete k values, all of those, he said, let's pretend they're all full. Consequently, if they are all full, don't know what they're full of, but if they're all full, then the next electron that wants to occupy a energy level must occupy a positive energy level, and that's why you can start filling in the slots at the positive side of the diagram, because these are all full. But of course, our argument that a photon can come in and hit a particle still applies. A photon can come in, give its energy to one of these particles in the Fermi sea on the negative side, and promote that electron to a position on the positive side. And in doing so, it will leave a hole in the space where an electron once was. And that hole, by comparison with all the other electrons around it, will be positive. Of course it isn't, because a hole is a hole, there's nothing there. But where something that used to be negative was, there is now a hole, and so by comparison with everything around it, that hole is positively charged. And what Fermi was able to postulate was, and I'm not going to pursue this because it gets more complicated, but this is just to give you the essence, that he therefore postulated that there could be a thing like an electron, but with a positive charge, that which we now know of as a positron. Now, nobody had ever heard of a positron before, but when the experimentalists went to look for it, they found it. They found a positron. And the positron was found because of Dirac's speculation that you could effectively extend these lines into the negative energy territory. And so his arguments were vindicated by experiment. And that, of course, is the way that all quantum mechanics is vindicated, because it accords with experiment. So now I'm going to rewrite the equations that we developed before. They're called Dirac equations. d psi right by dt was equal to minus v d psi right by dx. And the other one was d psi left by dt is equal to plus v d psi left by dx. And you'll recall that we cancelled them out, but I'm going to put back the I terms on both sides of the equation. And you'll just remember that v was equal to plus or minus omega over k. That was how we derived v. Now I can rewrite these two equations, which are, as it were, simultaneous equations. I can rewrite them in the form of matrix and vector by simply saying that that is I into psi right dot psi left dot. And just a reminder that psi right dot is a shorthand way of writing d psi right by dt. Right? Psi right dot is simply the derivative of psi right with respect to t. that's just a shorthand. And that equals minus IV into a matrix 1, 0, 0, minus 1 times a vector d psi right by dx, d psi left by dx. And if you multiply those through, taking the top and the bottom, you'll find that you'll get these formulae. I times psi right dot, which is that term there, is equal to minus IV, that's that term there, into 1 times d psi right by dx plus 0 into d psi left by dx. And that simply gives you the d psi right by dx. On the bottom, you're going to get I times psi left dot, which is d psi left by dt, is equal to minus IV times 0 times d psi right by dx, which is 0, plus minus IV times minus 1, which is plus IV, that's that, times d psi left by dx, which is that. So this is just a way of writing in matrix and vector form the two simultaneous equations above. And I'm going to call this matrix here alpha. Right, so we just remember that that matrix is called alpha. Now I just want to do a little bit of reminder for you that psi right we said was e to the I kx minus omega t, which meant that d psi right by dt was equal to minus I omega psi, and d psi right by dx was equal to ik psi. We did that just a little while ago. But we also said that psi left is equal to e to the I kx plus omega t, which meant that d psi left by dt was equal to plus I omega psi, and d psi left by dx was equal to ik psi. And that means that in respect of this equation here, for the derivatives of psi right and psi left with respect to time, I can put minus I omega psi and plus I omega psi. And for these two terms, I can put ik psi and ik psi. This, of course, is psi right and this is psi left. So if I rewrite this formula here, but putting in these terms here as substitutes, I'm going to get that I into minus I omega psi right, because that of course is psi right and that is psi left. So minus I omega psi right and plus I omega psi left, which is this term here, is equal to minus I alpha, because alpha, remember, is the matrix. Oh, there should be a V there, of course, but I'm going to set V equal to 1 to get it out of the way. So V equals 1. So I don't need a V there. So minus I alpha times these two terms here, which are these two terms here. So that's going to be ik psi right, ik psi left. Right, that's just rewriting the formula that we had above, but substituting the values that we have deduced en route. Well, I think you can now see that these are simultaneous, and what you've effectively got is that omega equals either plus or minus alpha k. Omega is, you've got an I on both sides, you've got an I inside, you've got a psi right inside. The only difference is that on this side you've got an omega, on this side you've got an alpha times k. So omega equals plus or minus alpha times k, depending on the top or the bottom. And we can sort that out quite easily by squaring it. So omega squared is alpha squared k squared, irrespective of whether you use a plus or a minus. And I want to park that, because now I want to ask the question, what about mass? Now our starting point here is what we learned in special relativity, and if you look at my 5 videos on special relativity in that playlist, I'm afraid you have to go all the way through to the 5th, where we derive that the total energy is equal to the square root of p squared c squared plus m squared c to the 4th. That's something that falls out of special relativity, and it's going to be the starting point for our consideration of the mass term. Now if I set c equal to 1, which is along the same lines as setting h bar equal to 1, get rid of the constants so they don't clutter up the place, then you can see that E is equal to the square root of p squared plus m squared. But p equals h bar k, and as we've said many times before, if you let h bar equal to 1, then p is k, so E is now k squared plus m squared. But I remind you that E is h bar omega, and again if you set h bar equal to 1, then E is omega, so that now gives me that omega is the square root of k squared plus m squared, and if I square both sides, omega squared is equal to k squared plus m squared. But just a little while ago, and I told you we were going to park it, didn't we show that omega squared is equal to alpha squared k squared? That's what we derived just a few moments ago. So from special relativity, we get omega squared equals k squared plus m squared, and from everything we'd done on particle physics, we got to omega squared is alpha squared k squared. So quite clearly, there's something missing. I mean, it's pretty obvious if you look at it that alpha squared has got to equal 1 because there is no component in front of the k squared term here. So we've kind of identified what alpha might be. Well, we know what alpha is because we've already shown it, and we'll need to show in a little while that alpha squared does indeed equal 1. But we need something for the mass. So let's try the idea that omega might equal not just alpha k, but beta m, where beta is also a matrix, and m of course is just the mass. Well, if that's the case, if we take omega squared, we're going to get an omega squared k squared term by squaring that. We're going to get a beta squared m squared term by squaring that, and then we're going to get a cross term by squaring. We remember that k and m are just numbers, but alpha and beta are matrices, so you have to watch what you do with matrices. So that's going to give us km, the numbers, into alpha times beta plus beta times alpha, where alpha and beta, as I say again, are matrices. And now I want to equate that equation with that equation. And from that I think you're going to see that if those two are going to be the same, the first thing you can say is that alpha squared must equal 1 because there is no component in front of the k squared. Beta squared must equal 1 because there is no component in front of the m squared. And this term here must equal 0 because it doesn't feature up here. And that essentially means that alpha beta plus beta alpha must equal 0. Well, now you have to do some mathematics to get that solution, and I'll tell you the answer. We already know what alpha is. Alpha squared will be, well, alpha, you'll remember, was 1, 0, 0, minus 1. And so we better check that that does indeed produce the answer 1, or in matrix terms, of course, 1 is the identity operator, which is the matrix equivalent of 1. So let's just do the calculation. 1 times 1 plus 0 times 0 is 1. 1 times 0 plus 0 times minus 1 is 0. 0 times 1 plus minus 1 times 0 is 0. 0 times 0 plus minus 1 times minus 1 is plus 1. That is the identity operator, the matrix equivalent of 1. Phew, alpha squared does indeed equal 1. Beta squared, if you calculate so as to achieve all these things here, beta squared turns out to be 0, 1, 1, 0, or that's beta. So if you multiply it by itself to get beta squared, That's going to be beta squared, and again we better just check it. 0 times 0 plus 1 times 1 is 1. 0 times 1 plus 1 times 0 is 0. 1 times 0 plus 0 times 1 is 0. 1 times 1 plus 0 times 0 is 1. That is the identity operator I. Beta squared does indeed equal 1. Thank goodness for that. Now we have to show that alpha beta plus beta alpha is equal to 0. So that's going to be 1, 0, 0 minus 1 times 0, 1, 1, 0 plus 0, 1, 1, 0 times 1, 0, 0 minus 1. That's alpha beta plus beta alpha. So let's work that out. We're going to get two matrices which we're going to need to add together. 1 times 0 plus 0 times 1 is 0. 1 times 1 plus 0 times 0 is 1. 0 times 1 plus minus 1 times 1 is minus 1. 0 times 1 plus minus 1 times 0 is 0. And on this side, 0 times 1 plus 1 times 0 is 0. 0 times 0 plus 1 times minus 1 is minus 1. 1 times 1 plus 0 times 1 is 1. 1 times 0 plus 0 times minus 1 is 0. These two are not the same. But what happens if I multiply inside and outside by minus 1? Then that becomes plus 1, that becomes minus 1, and this plus becomes a minus. And now I've got two matrices that are the same. This minus this is equal to 0. So alpha beta plus beta alpha equals 0, which is what we wanted. So now we can write the Dirac equation as I into psi right dot psi left dot, which remember are just the shorthand ways of writing the derivative with respect to time, is equal to minus I times v. We often set v equal to 1, but let's put it in full, times alpha, which is 1, 0, 0 minus 1, that's the alpha, times the vector, which was d psi right by dx and d psi left by dx. But now we need to add, and I haven't got room so I'll do it underneath, we need to add the m beta term. So it's going to be m, and then beta is 0, 1, 1, 0. And of course we'll need to act on just the psi right and psi left waves. So this is now the full Dirac equation. That's what it was before, but now we've introduced a new term which is going to accommodate mass. And let's do what we did before, which is to multiply through and get the two simultaneous equations that you can derive from this, simply by doing top and bottom. So let's start with top. I times psi right dot, which is what you get when you multiply the top here, is equal to minus IV times 1 times d psi right by dx plus 0 times d psi left by dx. So that's just going to give you d psi right by dx. What happens when we get here? It's going to be 1 times 0 times psi right plus 1 times psi left, which means you're going to get m times psi left. Oh, here we've got the right term, I psi right dot equals minus I v d psi right by dx plus m psi left. Psi left has crept into a psi right equation. Similarly, if you go along the bottom, you will find that I psi left dot is equal to plus IV d psi left by dx plus m psi right. And these are two coupled equations, they are called. And the interesting thing is that when you're dealing with the psi right terms, the mass term introduces an element of psi left. And when you're dealing with the psi left terms, the mass term introduces an element of psi right. And that is essentially the very starting point of a route, which we're not going to go down here, but that is the starting point of a route that would eventually lead us to the Higgs term and the Higgs boson. I have done a separate video on the Higgs boson. If we were going to go down this route, we would need to look at the whole problem of spontaneous symmetry breaking, which would not be appropriate at this stage, but possibly later on I'll have a go at seeing if I can do something along those lines to show how you go from here to the idea of the Higgs field. Meanwhile, I just want to very briefly touch on the fact that when we said that omega equals alpha k plus beta m, we were of course talking in one dimension. Suppose we are talking 3 dimensions, which I don't normally do because I keep it simple. But we just need to look at this briefly because we need to see how Dirac matrices are formed. What we would need to say is that omega is now going to be alpha x kx plus alpha y ky plus alpha z kz plus beta m, because now we're talking 3 dimensions. So these are the components of the overall coordinates. We would also of course know that k, from Pythagoras this is, that the total k squared would simply be kx squared plus ky squared plus kz squared. That's just Pythagoras. And now what we'll need to do, of course, is to, since we know that what we're trying to equate is that from special relativity, omega squared is k squared plus m squared. That is going to be one and the same as omega squared is this lot here, kx squared plus ky squared plus kz squared plus m squared. So that's this term here, all from special relativity this comes. But we've now got to take this term and square it in order to compare it to this term. Well, if you square something that's got 4 terms, you're going to get 16 terms. I'm just going to produce 4 of them. So I'm going to do omega squared from here, and I'm just going to take the squares of each of these. So that's going to be alpha x squared kx squared plus alpha y squared ky squared plus alpha z squared kz squared plus beta squared m squared. That's 4 terms plus 12 other terms, which you will get from squaring all of this. And now if you compare this to this, what you will see is that alpha squared must be 1 because there's no coordinate in front of the kx squared. Alpha y squared must be 1 because there's no coordinate in front of ky squared. Alpha z squared must be 1 because there's no coordinate. And beta squared must be 1. Well, we knew that from before. And the 12 other terms must equal 0 because they don't feature. So now we have to go to the mathematicians and we have to say we need to solve, we need matrices which equate to the fact that alpha squared is 1, alpha y squared, sorry, that's alpha x squared, is 1, alpha y squared is 1, alpha z squared is 1, beta squared is 1, and all the other terms, when you multiply them through, come to 0. What is the answer? And the answer will come back, you cannot do it with a 2 by 2 matrix. And you cannot do it with a 3 by 3 matrix. You will need a 4 by 4 matrix. So for beta, we'll need a 4 by 4 matrix. And it's handy to think of those as 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So they're going to be a 4 by 4 matrix. And for beta, the answer is that it's 1, 1, minus 1, minus 1, and all the other values are 0. And if you think about it, that is the equivalent of saying that this matrix, this 2 by 2 matrix in the top segment, that is just the identity operator. This in the top right-hand segment, well, they're all zeros. Bottom left-hand corner, all zeros. Bottom right-hand corner, that is just minus the identity operator. So you can represent, these are called Dirac matrices, they're 4 by 4 matrices for 3-dimensional space, and they represent beta, the mass term, and you can equally represent that as a 2 by 2 matrix, but each of the elements is itself a 2 by 2 matrix, if you see what I mean. When it comes to alpha x, that turns out also to be a 4 by 4 matrix. So it's going to have 1, 2, 3, 4 terms, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 4 by 4. And in this case, you've got 1, 1, minus 1, minus 1, and all the other terms are 0. And if you think about it, that can be represented as top left-hand corner is 0, bottom right-hand corner is 0. What is this? Do you recognise that? Well, that is simply sigma x, the old Pauli matrix, 2 by 2 Pauli matrix that we came across in quantum mechanics concepts. And this, of course, is simply minus sigma x. So alpha x, the 4 by 4 Dirac matrix, is made up of a 2 by 2 matrix which itself consists of 2 by 2s, and sigma x and minus sigma x are the valid parts. Well, I wonder if there's a pattern developing here. What about alpha y? Well, that too turns out to be a 4 by 4 matrix. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And that will have a minus I here and a plus I here, and a plus I here and a minus I here. And if you think about it, that is going to be top left-hand corner is all zeros, top right-hand corner is all zeros. This is simply sigma y, the Pauli matrix sigma y, and this is minus sigma y. See the pattern? So what is alpha z going to be? The Dirac matrix, 4 by 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And alpha z is going to be 1 minus 1 minus 1 plus 1. And that, if you represent it in the same form as before, top left-hand corner 0, top right-hand corner 0, this is now sigma z, and this is minus sigma z. So you can see the pattern for alpha x, alpha y, and alpha z, that alpha j, if you like, can be represented as 0 and 0, and then here you'll just use sigma j and minus sigma j, where j can equal x or y or z. So the Dirac matrix 4 by 4 will be determined by the application of the Pauli matrices, but when you go to beta, the 4 by 4 Dirac matrix for beta is just made up of the identity operators, plus and minus. So if we now go back to the Dirac equation in all its glory in 3 dimensions, we're going to get that I d psi by dt is equal to minus I, put the v term in if you like, times alpha j d psi by dx plus beta m psi. And that is the Dirac equation for 3 dimensions, where you need beta, you need 3 forms of alpha, alpha x, alpha y, and alpha z, each of which will take into account its respective Pauli matrix. If you work those all through, you will get a number of simultaneous equations. Same principle applies, you still have to solve them all, and this will take you en route to a mass term which ultimately leads to the Higgs boson. Hello, today we're continuing in our series on particle physics, looking in particular at annihilation and creation operators and introducing the idea of mass. Last time we looked very simply at the idea of quantum field theory, and I kept it simple so that this is an access point so that you can all find out more by looking at other videos or books. But we developed 2 field operators, and that was psi dagger and psi. Psi dagger is essentially the field creation operator. It consists of a plus, which is, as we showed, a creation operator, and a field. And the annihilation operator, which consists of, this is a field annihilation operator, which consists of a minus. We developed what that was last time. And a field. This is the field term. This is a sine and cosine wave. What is k in all of this? Well, remember that k is simply the what's called the wave number, and it is defined as being 2 pi divided by lambda, lambda being the wavelength of this wave. But we also showed that p equals h bar k, where p is the momentum, and so if h bar is 1, and we often set terms, that's how we represent the scattering. the incoming particle has been annihilated, the outgoing particle has been created. So if we put that in terms of the mathematics that we developed last time, what we can say is that this term, the psi dagger psi, will be, of course, the sum over k of, a plus k e to the minus I kx minus omega t. And this psi will be sigma over k a minus of k e to the plus I kx minus omega t. And that will all act on the state ki. Now it turns out that because we've got a time term in here, and because you don't know where this is going to happen in time, you have to integrate over time in order to get the full effect. And that acts on ki to produce kf. There is also, I should just say, what's called a coupling constant. I'll just squeeze it in here. Coupling constant g, which we won't need to bother with. It's also there as well, but that's not going to be any relevance to us at this stage. We're really interested in the total integral. And we learnt in quantum mechanics concepts of the inner product, which we wrote like that, and we said that an inner product of a ket vector with a bra vector, x and y, means this is simply the probability amplitude that if you prepare something in state x, this whole term gives you the probability amplitude of finding it in state y. And the probability as a whole will be the square of the probability amplitude. This was all described in great detail in my series on quantum mechanics concepts. So if this is not familiar to you, I suggest you go and look at that series so that you can see where all of this comes from. It's all explained very clearly. So consequently, what we can say is that I'm not going to worry about the probability. It's sufficient to look at the probability amplitude. The probability amplitude of taking a state in Ki and finishing up with a state in Kf, the probability amplitude of still was the proxy for momentum. And that particle is scattered off of the target with a different momentum, Kf, K final. And the target may well recoil. There may be just a slight movement, barely perceptible, because the target will be massive compared to the mass of the particles. But essentially the target absorbs any difference in momentum. So what do we do with this diagram as far as quantum mechanics is concerned? Well, it's fairly straightforward actually. What you have is you start with a particle in state Ki, that's this particle here, and you produce a particle in state Kf, that's this particle here. And how did you do that? Well, you, in quantum mechanics terms, field quantum theory, what you do is you annihilate this particle, so you apply the quantum field operator that will annihilate Ki, and then you put in the quantum field operator, the creation operator, that will create Kf. And in terms of quantum field theory, that's what has happened. This particle has been annihilated, this particle has been created. That doesn't necessarily mean that this particle has somehow vanished and another one has been created. But in mathematical h bar is 1, you'll find that in this series, in order to get constants out of the way, we set them to equal 1. So h bar and c, the speed of light, will often be simply regarded as 1. And so we don't need them cluttering up the formula. If you set h bar equal to 1, then p equals k, and that means that this term k is really just, this term k here and this term k here, these are really just proxy terms for momentum. So what these field operators are doing is essentially creating a particle with a momentum k, or annihilating a particle with momentum k. So let's now consider particle scattering, and I'm going to draw what's called a space-time diagram. So time goes along that axis and space along this axis, keeping it one-dimensional, of course. And I'm going to have a target which I'm going to place at space position x equals 0. In other words, it stands still, but of course it travels through time. Everything travels through time, but it doesn't move spatially, it just travels at the speed of time through time. And what we're going to do is to scatter a particle off of that target. So here comes a particle, and it has a momentum Ki, K initial. K, remember,